Let's look at a couple more situations for undetermined coefficients. So let's figure out what we should guess for this equation for our particular solution. Now, as we've seen, before you can make a good guess for your particular solution, you need to know what the complementary solution is. So let's go ahead and work that out. So the associated homogeneous equation is y double prime minus 2y prime minus 3y equals 0. The characteristic equation is m squared minus 2m minus 3 equals 0. This one factors, it's m minus 3 times m plus 1 equals 0. And so m is 3 and minus 1. And so the complementary solution is some constant times e to the 3x plus some other constant times e to the minus x. Okay, so now we can guess our particular solution. There are a couple ways to see what you should guess. So we have a polynomial added to an exponential. So you might think, well, maybe we should just make our guess for the polynomial, make our guess for the exponential, and then add them together. So since our polynomial is degree 1, we should guess a degree 1 polynomial. So that's ax plus b. Okay, and our exponential is e to the 2x, so we should guess something times e to the 2x. So that's c times e to the 2x. And notice that neither of these overlap with the complementary solution, so we don't have to multiply them by an extra copy of x. And since these two inhomogeneous pieces are added, we should just guess the sum like this. This will work, so I won't actually go through the calculation to find the unknown coefficients, but this guess will work. Another way to see that this is the right thing is to recognize that this equation is actually the sum of two different inhomogeneous equations, but with separate inhomogeneous pieces. So let me write out what I mean. So if we take 1/2 of the left-hand side, so 1/2 y double prime minus 2y prime minus 3y equals, and then just the polynomial piece, 4x minus 5. I need a parenthesis here. And also, for this first equation, what you would guess for your particular solution is ax plus b. And you would find a particular solution that looks like this. For the second equation, you would get 1/2 y double prime minus 2y minus 3 minus 2y prime minus 3y. So the same left-hand side, but with the right-hand side being 6e to the 2x. So for this equation, you would choose, I guess I need subscripts here, maybe y sub p1 and y sub p2. For the second equation, you would choose for your particular solution some constant c times e to the 2x. And you would find a solution of this form. So if you add together these two equations, you would add together these two particular solutions. And of course, the way I've set this up, right, I've put these 1/2s here, so that if you add these two equations, the left-hand side is y double prime minus 2y prime minus 3y, which is exactly the left-hand side we started with. And the right-hand side is 4x minus 5 plus 6e to the 2x, which is exactly the inhomogeneous term we started with. And your particular solution, your guess for a particular solution would be the guess for these two. So ax plus b plus c times e to the 2x. So either way you want to look at it, if your inhomogeneous term is a sum, then you just make your individual guesses and add them together. This is essentially an extension of the principle of superposition for non-homogeneous equations. All right, let's look at one more example of undetermined coefficients. So for this example, the right-hand side is tangent x. Let's see what we should guess for a particular solution. As usual, we should find the complementary solution first. So for this example, I'll let you work it out, but it turns out to be some constant times sine x plus some other constant times cosine x. Okay, so what should we make for our guess for a particular solution? Well, let's see. So probably we should guess, since we're starting with tangents, we should get tangents. But right, if we plugged this in and started taking derivatives of tangent, so we need some constant times tangent. If we plugged this in and started taking derivatives, we would be getting derivatives of tangent showing up. So we need something to cancel those derivatives of tangent. So we should put the derivative of tangent in here as well. And the derivative of tangent is secant squared. But then if we put this into the differential equation, we'd get derivatives of secant squared showing up. So we need a term with the derivative of secant squared to cancel the stuff that you would get by plugging the secant squared into this left-hand side. And the derivative of secant squared, well, it's going to be, it's some constant times, turns out it's secant squared times tangent. But if we plug this into the differential equation, we get the derivative of secant squared x times tangent. So we get more stuff that we'd have to cancel. But then if we plug that in, we'd get even more stuff. So we have this sort of infinite chain of terms. And so this particular solution, it's, right, I mean, how do we make sense of this infinite sum of functions? It's not clear that this infinite sum of functions even means anything. And so we really don't have a good guess for what the particular solution should be. Right? If you look back at the previous examples of undetermined coefficients, this big chain of derivatives, right? Every time we had something on the right-hand side, we threw that in here, and then its derivative, and then the derivative of that, and eventually this big chain of things stopped or started repeating itself, so that there was only a finite list of undetermined coefficients. But for this particular inhomogeneous term on the right-hand side, the chain of derivatives gives you an infinite number of undetermined coefficients that you would need to figure out. And that's just not going to happen. I mean, even if you could take all the derivatives here and set up the system of linear equations to find the undetermined coefficients, you'd have an infinitely large system of linear equations to find the unknown coefficients. So this isn't going to work out. So for this kind of inhomogeneous term, where its list of derivatives doesn't sort of loop back on itself, undetermined coefficients isn't going to help. So undetermined coefficients is not a panacea that lets you find a particular solution for any kind of differential equation with an inhomogeneous term. It only works for some inhomogeneous terms.